friends, welcome back to our channel Abi Chemistry tutorial. So in this video we are going to learn BAEYER Villiger oxidation or BAEYER Villiger rearrangement. So already we are learning a series of organic naming reactions and this is one among that, and if you have not checked the other videos in this playlist, that is organic naming reactions, you can check the videos. The link is given in the description box, and we also have many structural elucidations and many useful videos which will be highly useful for your BSc, MSc degrees. This BAEYER Villiger oxidation you will be learning from the 12th standard itself, so this reaction will be helpful for the 12th students and BSc, MSc and any students preparing for PGTRB or any other competitive exams. So let us learn the reaction, and before going into the video, if you have not subscribed to our channel, please take a second to subscribe to our channel and share to all your friends. And now let's get started. So what is BAEYER Villiger oxidation? It is the oxidation of ketones to ester using pair acids. So what are pair acids? So if we have COOH group, that is if we have COOH group, we say it is carboxyl group and this is an carboxylic acid. If we have COOH, so this is pair acid. So this oxygen is extra, so we say it as pair acid. So the oxidation reaction, the oxidation of ketones to ester using pair acids is called BAEYER Villiger oxidation. So this is the reaction, general set of reaction. So this is a ketone, as you can see, two alkyl groups with the carbonyl group at the middle. So it reacts with pair acid, that is per-benzoic acid. This is per-benzoic acid. So phenyl group we have here, no? So it is per-benzoic acid to give an ester. Okay, so we get an ester here and the benzoic acid is the byproduct we get. So if we use cyclic ketones, the product will be lactones. So here I can see this is the structure of a lactone. Here in this case we have used peroxy trifluoroacetic acid. So 3 fluorines are here in the place of acetic acid's hydrogens. So 3 hydrogens of acetic acid is replaced by 3 fluorines. So it is called peroxy trifluoroacetic acid. So the best oxidizing agent used for BAEYER Villiger oxidation is peroxy trifluoroacetic acid. Some other peroxy derivatives are also used for the purpose of BAEYER Villiger oxidation, and they are per-monosulfuric acid, which is also called as Carros acid, and per-benzoic acid, as we studied in the first example here, and per-acetic acid is also used for BAEYER Villiger oxidation. So next we have to look into the mechanism of BAEYER Villiger oxidation. So this mechanism can be studied in a single series of reaction, and the basically two things happen, that is 2 steps actually. So that we have explained in words first. So the acid catalyzed addition of pair acid will take place to form an intermediate peroxide. So this is the thing you have to keep in mind, acid catalyzed addition of pair acid. So pair acid adds to this ketonic group by acid catalysis. So an acid should be used and the product will be intermediate peroxide will be formed. And this peroxide undergoes rearrangements and finally we will get the ester. So what is the mechanism? So first the acid catalyzed addition of the pair acid takes place to form a peroxide, that is the intermediate, and this intermediate follows some sort of rearrangements that I will explain later, and the rearrangement will give the final product ester. So this is the mechanism. So this is the ketone RCOR, R dash, this is another group, R dash, this is R alkyl group and this is another alkyl group. So now acid catalyzed reaction takes place. So acid catalyzed means it adds a proton to the ketone. How it acts? So here you can see this double bond shifts over this oxygen. So this oxygen will gain a negative charge. So this H plus goes here and it will add to this O as OH. And since one bond is shifted over this oxygen, this carbon will get a positive charge. So that is why this carbon has gained a positive charge and this hydrogen is attached to this oxygen. And this acid catalyzed addition of perbenzoic acid, right? Per acid. Here we have used perbenzoic acid. So let us see how this perbenzoic acid gets attached to this carbocation intermediate. So here this per acid splits here. So it will split into H plus and this will split as O minus. Okay, so PHCOO minus, and here we have a positive charge. So this positive charge and this negative charge, that is this negative charge will attract this positive charge and this will form a bond here. So here you can see this carbon forms a bond with this oxygen and here you can see OO C double bond O phenyl group. Okay, so this is the peroxide intermediate. So this is the peroxy group and this peroxy group is added to this carbocation and so this product is called the peroxide and this is the intermediate peroxide formed here. This bond shifts over this oxygen, so this will become a negative charge and this group is completely removed from this intermediate. So finally, since one bond is removed from this oxygen will become positive and this oxygen becomes electron deficient. So here you can see that. So this group is completely removed and this oxygen will get a positive charge since it's one of the bonds is removed. So now a sort of rearrangement takes place. So I told it is the rearrangement of a group from carbon to the electron deficient oxygen. So this intermediate will be followed by a rearrangement of a group from the carbon to the oxygen. So carbon to oxygen. So how it takes place? So clearly you can see. So this is R dash group, right? So this is the alkyl group and this oxygen is electron deficient. Here you can see it clearly. And this is electron deficient. So this bond of this alkyl group completely shifts from this carbon. So this will get a negative charge and this group is shifted to this electron deficient oxygen to form OR group. Since this bond is removed from this carbon will become electron deficient now. So this carbon is getting a positive charge. So that is what represented here. So this will exist in an equilibrium situation. So here you know this oxygen will have four electrons, that is 2 pair of electrons. So this pair of electrons will be shifted over this between this oxygen and carbon to form a bond. So here we get a double bond. So this carbon's valency will be satisfied and this oxygen will get a positive charge. So this is a resonance structure here. So this set of electrons will be shifted between this carbon and oxygen to form a double bond. So the carbocation is satisfied. Since one pair of electron is moved from this oxygen, so this oxygen becomes electron deficient and this will get a positive charge. So the last step is the removal of hydrogen so that we will get a neutralized product. So here we will remove a H plus. So this bond will satisfy the valency of oxygen. That is, this will move over here and the positive charge will be neutralized by this set of electrons and we will get the neutral product ester. RC double bond O, OR. So this is an ester. So I hope this will be clear for the mechanism. So this is the ketone. So the acid catalyzation takes place. So this H plus is attached to this oxygen. So this bond shifts over here. The H plus comes here. So this carbon will get a positive charge. Here you can see. Then we add the perbenzoic acid and this bond shifts here. This bond breaks here and the H plus goes out and this will get a negative charge. And this negative charge get attached to this carbocation position and here you can see this is the product. Peroxy intermediate. And now this peroxy intermediate Now this bond shifts over this oxygen, and this group is completely removed, and now the oxygen becomes electron deficient with positive charge here. Okay, so now rearrangement takes place. Rearrangement of the intermediate takes place by the transfer of a group from this carbon. That is, this group R dash group is completely removed as negative charged ion, and it attacks the electron deficient oxygen. So now the carbon becomes electron deficient, so it will become positive charge. And here a resonance form occurs, that is, this set of electrons from this lone pair of electrons from this oxygen shifts over here to form a double bond, so that the positive charge is neutralized and the oxygen becomes electron deficient, so it becomes positive charge. And now to neutralize the molecule, the H plus ion will be removed, and this bond shifts over here to neutralize the positive charge, and we get a ester. So this is how the BAEYER-Villiger oxidation takes place, or this is also called BAEYER-Villiger rearrangement. And experimentally it is noted that the oxygen atom in the ketone remains the same in the ester also. So that is, the oxygen atom in the ester is from the ketone and not from the perbenzoic acid. So since here we have used labeled oxygen at this position, carbonyl group, and that carbonyl group remains the same in the product also, because the oxygen 18 or the radioactive oxygen remains the same in the product also. So it is proved that the oxygen atom from the ester is from the ketone and not from the peracid. So now we will learn about the applications of BAEYER-Villiger oxidation. So already we know it is the simple method of preparation of ester. So the first thing you can do is ester. So this is a ketone. When you use peracids, we get ester. And you know, ester on hydrolysis usually produce an acid and an alcohol. So this is an acid and alcohol. So BAEYER-Villiger oxidation can be used to prepare ester and also acids. So BAEYER-Villiger oxidation can also be used to prepare anhydrides. Alpha diketones or orthoquinones can be treated with peracids, so that you will be getting anhydrides. So I will show you a few examples. So this is the first example, alpha diketones. So two ketones at the first position itself. So to alpha to this we have a ketone, from this functional group alpha to this carbon we have ketones. So alpha diketones, when treated with peracids, one more oxygen is introduced in between these two functional groups, that is called acetic anhydride. This is an anhydride. And this is also orthoquinone. So here also you get an anhydride by introducing an oxygen in between these two carbonyl groups. So the third application of BAEYER-Villiger oxidation is the preparation of lactones. Cyclic ketones. If we treat cyclic ketones with peracids, we get lactones. So this is a cyclic ketone. This is cyclohexanone, and this is treated with peracid to form a lactone. That is, one more oxygen is introduced in between these two bonds. Here an oxygen will be introduced. So this is called O-caprolactone. So this is all about BAEYER-Villiger oxidation, and I hope the video is highly useful for you. So you can use these notes for your 12th or BSc or MSc final examinations, and you can also use these notes for preparing for your competitive examinations. So I think this video helped you a lot. So please hit the like button, share to your friends and whoever you think they will need this video. And don't forget to subscribe to our channel. So see you on the next video. Until then, bye. Thank you. Take care.